Welcome back everybody. So today in the lecture 2 we will like to continue where we left off in the quantum mechanics in the relativistic regime course essentially. So what we were doing in the previous lecture was we were covering various aspects recapping non-relativistic quantum mechanics essentially. We covered wave particle duality, okay, what is the de Broglie wave particle duality. Then we introduced Schrodinger wave equation, and then we introduced linear superposition principle, okay. So on, so we can okay, just to recap essentially, and of course we remember that it is 100 years since quantum mechanics was born, and we had wave particle duality, and then we introduced the Schrodinger equation, and then we introduced the linear superposition principle, which satisfies the Schrodinger which says that if there are two solutions, independent solutions of the Schrodinger equation, the linear combination of them is also a solution of the Schrodinger equation. And then we introduced wave packets and uncertainty principle, okay. The width of the wave, the product of the widths of the wave packets in the momentum space and position space is always bounded by below by h cross. And then we also demanded that the wave function and its first derivative should be continuous in all space time points. And then we introduced the concepts of scattering states and bound states. With this we have the enough armory to attack problems with simple potentials, okay. Of course in the quantum mechanics class, non-relativistic quantum mechanics class, I think you must have done several potentials, okay, including the step potential, the barrier, the step well, the delta function potential, the chronic pinning models, and so on, and then hydrogen atom angular momentum and so on. So what we will do is we will take one of the first simplest potentials, okay. In this class essentially we will just take a very simple potential and try to solve it in great detail. I want to do it, I know that most of you know this potential very well. It is a very easy potential which is called a step potential, and most of you must have done it several times and you know how to solve it and everything, but I want to go through it again in sort of in some detail, so that in future I want to repeat the same exercise in the relativistic case essentially, okay. And after doing that I will cover the rest of the potentials very fast, meaning I am not going to go into the details of each of these other potentials. I will just tell the results and so on. So the potential we are going to consider here is called the potential step potential. So initially we had to set up the potential where it is located and so on. So we located the step potential V, it is a one dimensional problem. So it is only there is only one direction, which is x direction, and the step potential happens, let me see if I can change the color. So it is 0 all over here, and then it has a height of V0 at x is equal to 0. This is negative x direction. So this has a height V0 and it goes all the way up to infinity essentially. Okay. So this potential algebraically we can write it as V of x is given at 0 when x is negative and V0 when x is greater than or equal to 0 essentially. Now classically this is a very simple one dimensional problem. Essentially what happens is, depending upon the energy of the particle, if it has energy greater than V0, classically what happens, classically here means okay, in non classical mechanics, the particle with energy greater than V0, much greater than V0 will not see the potential, it will just pass through, okay. There is no reflection, and if the energy of the particle is less than V0, it gets completely reflected. That is what happens, okay. E greater than 0, full transmission, so it is completely transmitted. On the other side, essentially E less than V0, it gets fully reflected. So this has when it is transmitted, the energy of the particle when so it has, it is a full scattering problem. So the energy of the particle, okay, here is reducing from the momentum of the particle is reducing in this case from P is equal to root 2 mv E at x less than 0 to P is equal to root 2 m E minus V at x greater than 0. So with reduced momenta, this particle is transmitted, just a simple scattering problem in scattering, okay. Now we have to set up the Schrodinger equation in this case. So we do this. So in the two regions, okay, we can write the Schrodinger equation as follows. For x less than 0, we write it as d square by dx square, it is a time independent problem, k1 square psi 1 of x is equal to 0. At x greater than or equal to 0, we have d square by dx square plus k2 square psi 2 of x is equal to 0. Here in the above, k1 square is equal to 2 me by h cross square, and in the case of k2 square it is equal to 2 me E minus V0 by h cross square. So this is simple, it is a simple one dimensional problem, it is time independent, so you can solve this essentially. Now the most general solution, the way we solve it is, you consider the most general in the two regions are just plane waves essentially, in fact nothing else, okay. So what you have, you can write it down, psi 1 of x is equal to a e power I k 1 of x plus b e power minus I k 1 of x for in the region x negative, and psi 2 of x is equal to c e power I k 2 of x plus d e power minus I k 2 x, x greater than 0. Now the A component and B are essentially constants. This is in the this part is in the positive x direction, this part is in the negative x direction, the wave part which is travelling in the negative x direction. This part is in the positive x direction in the x greater than 0, and this part is in the negative x direction. So these are backward moving waves and these are forward moving waves essentially. Now we will consider the case where the wave is starting from the x direction, negative x direction, hitting the barrier, okay, and then passing through it essentially. So this is the kind of situation we will consider essentially. So for this we have to consider what is the energy of the wave essentially. So first we will start with the case where energy of the wave is greater than 0, okay, the case where energy of the wave is greater than 0, and that is precisely what we have been doing here. So we assumed here E is greater than V 0. Okay. So with this now what we can do, we can write, go ahead and set d is equal to 0, because we are assuming the case when the wave is coming from the left essentially. So with this we have psi of x t is equal to a e power I k x minus omega t plus b e power minus I k 1 k 1 x minus omega t for x less than 0, and this is just c e power I k 2 of x minus omega t. So we have, this is the incident wave, b is the reflected wave, c is the transmitted wave essentially. So just to write it down, this is transmitted, reflected, incident. This is in x greater than 0 region essentially. So we can actually calculate the probability density. The probability density is given by mod psi x square in a given region of the parameter space. So you can plot this probability density in the potential plane. So we have V of x, in this case the probability density will look like in this case there is an oscillator ring, because it is lambda 1 is equal to 2 pi by k 1 and lambda 2 is equal to 2 pi by k 2, and as you see in the x greater than 0 case, in the potential case, psi 2 of x is a transmitted is nothing but mod c square. Actually you can calculate it and see that psi 2 of x, if you take psi 2 of x mod c square, it is just the probability is just a straight line, it is a constant. So it just becomes a constant essentially. Okay. Now given this thing, I want to one wants to calculate what is the reflection coefficient and what is the transmitted coefficient. And this will tell you the difference between classical physics and quantum physics. So again I am emphasizing that we are always considering E greater than V 0 case essentially. We are always considering V greater than V 0. So in the classical limit it will just pass through, there is no reflection coefficient in the classical limit. In the quantum physics case this changes essentially, as we will see. So to calculate the reflection and transmission coefficient, I need to define what these are. So the reflection coefficient is defined by coefficient R is equal to reflected current density by incident current density which is also sometimes called J reflected by J incident, and the transmission coefficient is similarly defined as J transmitted by J incident. Okay. So, let us calculate what this JR, JI, JT are essentially, which are essentially the current densities for the reflected wave and the transmitted wave and the incident waves essentially. So, the current densities, as you know, this is also important, for the incident wave is IH cross by 2m. This can be got by your continuity equation. This is a part of your continuity equation, which is psi incident of x by d psi star incident of x by del x minus psi incident star of x by d psi incident by dx. Now, for the reflection current density and the transmitted constant density, you just replace by incident with the transmitted and reflected essentially. Now, what is the incident wave? The incident wave is this one. So, what we have seen earlier essentially. So, in this part, this is the incident wave essentially, this is the incident wave. Okay. So, we can substitute what is the incident wave into this expression and get the what is J, this thing J incident. So, this is given by, if you substitute it, it gives you H cross k 1 by m mod a square. Now, similarly, you can do what is J reflected, and it turns out J reflected is given by H cross k 1 minus m by mod b square, and similarly you have J transmitted H cross k 2 by m by mod c square. So, with this you can define, you have all the quantities now to define what is the reflection coefficient, what is the transmitted coefficient. So, this is what we are going to do. Okay. So, we will calculate, we will define what is the reflection coefficient. So, the reflection coefficient comes out to be, like I said, it is J reflected by J incident. So, J reflected by J incident. Now, we calculated J incident and J reflected, just substituting back into this, we get mod b square by a square. So, this matches. Okay. So, this H cross k by m 1 would cancel and there is a modulus. So, this is just mod b square by a square. Okay. J transmitted transmission coefficient is k 2 by k 1 mod c square by mod a square. Okay. Now, these are constant. These there are 3 constants now, which are a, b and c, which have to be determined by the suitable choice of the boundary conditions. So, we have to impose certain what is the boundary conditions which we had to impose, such that we can determine what these constants are essentially. Okay. So, we got this reflection and transmission coefficients, and now we have to make sense out of them. So, to make sense out of them, what we will use impose is, like I said, we will impose the condition of boundary conditions. So, the first one is the boundary condition that the wave function should be continuous at 0, because 0 is the place where there is the potential essentially. We at 0 at x is equal to 0 there is the potential which goes with the height of V 0. So, psi 1 of 0 should be equivalent to psi 2 of 0. So, that is the first condition, and substituting this we get in the A plus B is equal to C. This is easy to see, which we can see. Okay. We have defined so x is equal to 0 e power I k s, this just goes to 0, and A plus B is equal to C. And the second boundary condition is on the first derivatives. So, the first derivatives, so the second condition is d derivative at x is equal to 0 on psi 1 also should be continuous. So, this gives the condition k 1 a minus b is equal to k 2 c. Now, using this, so there are these two equations, you have k 1 a minus b and this, and a plus b is equal to this. So, you can derive, you can get the relations that you can solve for b to be in terms of a k 1 plus k 2 to a, and c is also given in terms of a k 1 by k 1 plus k 2 in terms of a. Now, you put back into your reflection and transmission coefficients, and you get the expressions that r is equal to k 1 minus k 2 whole square by k 1 plus k 2 whole square, and the transmission coefficient is 4 k 1 k 2 by k 1 plus k 2 whole square. Now, compared to the classical physics, what is the new thing in this picture is that the reflection coefficient is non-zero. So, even when the potential the energy of the particle is much larger than the potential, there is still a non-zero probability that the particle is reflected, a part of the particle is r is not equal to 0 unless k 1 is equal to k 2. Okay. That only happens V is equal to 0. Okay. So, as long as V is non-zero, there is always a reflection coefficient in the quantum physics essentially. So, which tells you that quantum physics is different from mechanics result, from classical physics essentially. Okay. So, this sets it apart. So, what happens in the other case essentially? In the other case, what happens if E is less than V 0? Okay. So, in the other case E less than V 0, we will follow, I will not go to the entire derivation essentially. In this case, the second part of the equation is no longer oscillatory, because at x less than 0 the incident wave is the same essentially, the incident wave will be roughly the same essentially. So, we have psi of x t would be a e power I k x or k x k 1 x minus omega t. Okay, we can just set it to be that, plus b e power minus I k 1 x plus omega t. This is right moving, left moving, same as previously, nothing changes in the incident part, okay, and the reflected part, nothing really changes in the way we write the expression essentially. But because E is less than V 0, So, what changes is the second part of the equation. So, this will become at x greater than 0, this will no longer be oscillatory, but it will be an exponential solution e minus k2 prime of x e power I omega t, where x greater than or equal to 0. Okay. So, what is k2? Okay. K2 is v minus e 0, okay. V minus e k2 square is equal to v minus e, okay, by h cross square. So, unlike the previous case, essentially we had just to see, the only thing is the transmitted part is changed essentially. So, in the earlier case we had two m v okay, there is a 2 m essentially k2 square, here it will be e minus v 0, okay, it changes the sign essentially, there is a mass term also. Maybe I will write it down again. So, this modifies sorry, v 0 minus e, I am writing down the same expression. So, this modifies the oscillatory part into an exponential part essentially. Now, you calculate everything in the same fashion, okay, and you use the same boundary condition, follow the same procedure, which I will not repeat, as above, okay, except for this thing essentially. And in this case what happens is, when you solve for b, it comes out to be k1 minus I k 2 prime, which is this, by k1 plus I k 2 prime times a, okay, and c is equal to 2 k1, there is no k2, remember that k1 plus I k 2 prime times a. So, you can solve this essentially, and then when you calculate the reflection coefficient r mod b square mod a square is equal to k1 square plus k2 prime square is equal to k1 square plus k2 prime square is equal to 1. And we also have the transmission coefficients to be ending up to be 0, r plus t is equal to 1, the reflection plus the coefficient. Now, these are important for me, I want to emphasize that there is 0 transmission, okay, and this is exactly like the classical cases, exactly like the classical case. Like we mentioned in the beginning of this lecture essentially, okay. But the important thing is r plus t, the reflection plus transmission coefficient is equal to 1, and what we will see later on, why I am emphasizing this again and again, is that when we recap the same example in a relativistic sense, you see violations of this r plus t is equal to 1 all over the place essentially with simple potentials. So, all through we have considered non-relativistic energy momentum relation, which is given by E is equal to p square by 2 m plus v, okay, which is given by E is equal to p square by 2 m by v, okay. That is essentially the emphasis of the Schrodinger equation. So, the Schrodinger equation I wanted to write in that particular fashion is because we are starting with a non-relativistic energy momentum relationship. Now, if you start with this non-relativistic energy momentum relationship and consider a simple step potential, say for example everything is well behaved, you get some quantum mechanical features, like if E greater than 0 you get a reflection coefficient which is non-zero, and but always r plus t is equal to 1. Here also in the previous case also, where is the previous case? Okay. So, here also r plus t is equal to 1. So, you have reflection coefficient plus transmission coefficient is equal to 1. Okay. So, the reflection coefficient is non-zero compared to the classical, so it is a quantum mechanical result, but still it does not stop that this is non-trivial results essentially. It is well behaved, everything is well behaved, you can actually make predictions and calculations. Now, the same example as we will see later on is that if you do it in a relativistic energy momentum relation, using a relativistic energy momentum relation, we will go completely haywire, and that brings up one of the first pathologies of relativistic quantum mechanics or quantum mechanics in the relativistic sense essentially. So, I will stop here, and in the next class I will continue doing the revision of some salient features of quantum mechanics. I will do angular momentum, spin, and then hydrogen atom, harmonic oscillator. So, these are the basic stuff we need, okay. And then I will continue with non-relativistic quantum mechanics with path integral methods, and then I will do the recap of special theory of relativity, and that is the modular structure essentially, okay. And then we will start with our first example of relativistic quantum mechanics essentially, relativistic wave equation and the study of quantum mechanics. Okay, I will stop here. Okay, thank you. Yeah.